Thank you, Mark. Are you able to hear me all right?
I can.
Good. Well, Brooke, Mark.
Just a moment, just before we start. Brooke urged me, and I forgot. If everyone out there can mute their microphones right now before we start, it saves a lot on the echoing effect and also embarrassing moments you might have at home. If you do that, otherwise we're ready to go.
Thanks, Mark, and thanks, Brooke, and Andrew, looking forward to your presentation. I just wanted to take this opportunity to say a couple things. One is just thank everybody for managing work and family and all kinds of situations. This is an incredibly stressful time with COVID-19. I think it's important to recognize that it's really hard to sort of manage your work in a new telework environment at the same time as you have loved ones at home and school kids at home and elderly parents and navigating just life in a new environment and having the flexibility to give everybody a little bit of space and a little bit of extra time if a person needs it, or a chance to back off and have an understanding if things need to be rescheduled is really important to do that. I was thinking about this yesterday as I was talking to someone, and I often heard about the culture at the PCA, and having only been here about 15 months, I heard that and how it was a family. And at times like this, when you get into sort of stress, you see the culture come through. And my experience so far, both at the management level and at the staff level, is that culture is really strong and has allowed, I think, work to function well, for friendships to continue on, for humor and colleagues to work with one another in a way that, you all who have been here a long time maybe know that intuitively and have seen it throughout your careers or even your times on your floors. But for someone from the outside, it's times of stress that you see how people react and organizations are created and maintained in the fabric within them. And I see that in spades through here. So that's just a big shout out to all of you. So just thank you for all the great work and being able to manage through this. If I can just say one thing, I am delighted to be able to listen in and participate in these meetings. One of the things that I think the pandemic is having a huge impact on the environment, and probably all of you have been able to see that, whether you're looking at, the impact of images of the Venice canals and the crystal clear waters there, or major decrease in air pollution when you take a look at Beijing and Shanghai and even Los Angeles. It's really just remarkable. And for me, coming on the heels of Earth Day yesterday, what it represents is we can make a huge difference, and a lot of times you hear criticism about, well, there's nothing we can do, or how can we retard and climate change and greenhouse gas emissions and pollution of the environment and individually. And yet when you have an opportunity like this to sort of test that method out and to see the impact that human behavior has on the environment in a very short period of time, extraordinary short for scientists like all of you are, to me, it just gives incentive and it gives motivation that we can address these. And I was trying to think about sort of from the groundwater standpoint, and I asked Katrina Kessler, the Assistant Commissioner of Water, yesterday to take a look at what working with Pam and with Catherine and some of the others people who do the groundwater and the surface water monitoring programs, to take a look at how can we sort of see a before and after impact of COVID on our water quality and our water resources in the state, and what we already do in that respect, that this is just easy, or what we can do now to see what those changes are. Because I'm a firm believer that the science and the data can drive changes in behavior and legislative action. And we have a unique opportunity at this inflection point to see how this impacts us. And I honestly do not mean to trivialize the human impact, the human toll by any stretch, but I also applaud our effort, to take a look from science and data as to what changes we can make and how we can demonstrate that with these changes, we can bend the inflection curve on pollution from all the different media. So I'll stop rambling, but just say, Andrew, I'm excited to see the discussions you have, because this sort of movement and interact with surface water and groundwater, it just comes up all the time, even at the things that I deal with, whether it's dealing with the initial twin metals mining up on the boundary waters and the issue of groundwater and surface water interaction is front and center to that pre-environmental impact statement scoping document. I see it there. I just had a discussion with DNR on that last week. And so it's timely for me to learn a lot. And thank you for inviting me to listen in.
Peter, hey, thanks so much for the remarks. That's great. We'll have to have you do all of the introductions to our talks. That was quite
well.
And thanks for the words of confidence. They're good to hear. So yeah, we are going to hear from Andrew Streitz, who has had a long and storied career with the MPCA. Anyone who has been around the MPCA knows. And it's a talk that I've been looking forward to hearing for a few weeks now. He's going to talk about paired water sampling he's done to show surface water groundwater interaction. And in this case, he's going to be talking about, as you can see, chloride through groundwater and into surface water. Andrew, it is great that you could join us this morning remotely, and have at it.
Well, thank you both, Peter and Mark. When Mark told me that we were going to do this talk, after all, even during the pandemic, he said something about that I'd be the lab rat. We'd test out to see if this worked. And I thought that sounded fine until I remembered that most lab rats die from the experiment. So I'll do my best in any case. Let's see if I can advance this. Tell me, we might have some issues here. Did that work? Okay, outline for today. I give you the stunning news that chloride is an agency priority. Brooke, withhold your laughter. Also that chloride has both urban and rural sources. Groundwater network studies the movement of compounds through our water resources. You may not have known about that bit. And that field and laboratory data can be used to show how chloride moves from the land through groundwater and into surface water. I'll be sharing a lot of data with you today, and hopefully I'll make it clear that it does represent something important. So I appreciate your patience. This is taken from our own website. And I think when most people at the agency and outside the agency now think of excess chloride in the environment, they think of de-icing. And that's because it's a big problem and it's mostly an urban problem where most of us live. But we don't think about the rural site, the rural side of things. And most recently, the agency has been investigating excess chloride from water softeners and farming practices. And I'm focused today on the rural settings. Old softeners used a lot more salt than newer ones, and chloride can be found in all sorts of farm chemicals as well as feedlot manure. And another helpful page on our website quantifies this for you, and you can see that more than a quarter, close to a third of all of the excess chloride comes from farming rural practices. So, Groundwater Network. It all started about 10 years ago when my supervisor at the time, Steve Thompson, challenged me to design a way to study groundwater surface water actions and, oh yeah, do it on the cheap. Now, many of you are aware that groundwater and surface water interact, that they're dynamically linked, but we lacked the means to study it. That's when we heard about a DNR program called the Sentinel Lakes project. And it's a very interesting study that looks at lakes across the state, and they are in all major land types, of Canadian Shield to through forest to prairie and corn belt, and they're also shallow and deep lake. lakes in each of those areas, as well as deep water, cold water lakes. I continue to work with the DNR and the Sentinel Lakes coordinator, Casey Schoenberg, who has been very generous with his help. So I wanted to point that out. So because all these lakes were being intensively studied, I could put wells around selected lakes and have most of the work already done on the surface water side. All I needed to do was take care of the groundwater side. So I chose 4 lakes: Bearhead Lake in northern St. Louis County, Pearl Lake in Streitz County, Madison in Blue Earth, Chocatan in Lincoln. That's the lake that I'll be discussing today. It's important for me to say at this point that this small network that I set up is a small part of the groundwater monitoring we do at the agency. It's part of the larger ambient groundwater network that is run by Sherry Croning, and I receive a lot of help from her, David Duffy, and my supervisor, Eric Smith. So just to get this out of the way, the way everything moves around, that water moves into groundwater and then into surface water and returns to the atmosphere through the water cycle. And precipitation falls, there's infiltration into groundwater, and this is a water table system that I'm describing. Once water reaches groundwater, it discharges almost always to surface water, to a lake, and then returns to the atmosphere through evaporation and transpiration.
Hey, Andrew, we have a question on the chat if you want to take that now.
Sure. What's up?
Is there a specific definition for Sentinel Lakes?
Well, Casey would have to tell us what the genesis of that name is, but what the DNR was looking for was trying to get a handle on what's happening to our lakes, to go to lakes, some of which had been affected by human activities and some that hadn't been affected, so that we'd have the data in hand to make judgments. Much like Peter mentioned, that we're going to be in a position to understand how our absence from the environment for a few months, we hope, affects the quality. By having a long-term baseline for studying of these lakes, we'd be able to see changes, perhaps climate change, perhaps farming practices, perhaps sanitary districts, industrial processes. So that's the intent of using the name Sentinel, I believe. There are several methods I use to study groundwater surface water interactions, and the first is physical sampling. And one of the real strengths of this project is that we have paired surface water and groundwater sampling. That means that when a sample is taken from the lake, while the boat is still dripping with water, the sampler is visiting the well on the shore of that lake and taking a sample. So that builds a very powerful data set, and we've done this for 8 years, 6 times a year, in months May through October. Right here you see the Chocatan shallow well on the south side of the lake, and the sampler is pumping 3 well volumes from the well. That's so that the water that's in the well when we take samples is not stagnant water, but it is water that's been pulled in from the aquifer and is therefore representative of the geochemistry of the aquifer and the elevation of the aquifer, groundwater elevation. Luckily for me, this work is carried out by Pam Anderson's surface water monitoring section and Lee Engel's unit. They've been very helpful in incorporating my groundwater monitoring into their regular schedule. Thanks also to Jesse Anderson for his guidance on lake science. So the samples are submitted monthly for groundwater and surface water for general chemistry parameters. That includes phosphorus and chloride, which I'll talk about today, and metals. This is a cross-section of what it looks like to see a well in the ground. And the other way that I collect data, besides physical samples, is DownHold Meters. And they are cigar-shaped, cigar-sized, completely self-contained meters. They're waterproof. They have power. They have memory and storage, and they're suspended from the well cap down to the well screen to collect data. They are autonomous for up to 5 years, although I visit them every year to download data, to check the crimps for corrosion, to make sure that the software is working the way it's supposed to. The transducers I place down at the screen collect groundwater elevation information, water temperature, and conductivity, and the transducers that are above the water level collect barometric pressure and ambient temperature. So onto the site. This is Shakatan in Lincoln County. And if I extended the view just a little bit to the west there, you would see South Dakota. So this is right on the border. I pronounce it Shakatan, and I spell it this way. I was instructed in this by the county commissioner in Lincoln County, who gave me permission to put in my well, and I'm a very loyal hydrologist, so that's how I do it. But you'll see it spelled and pronounced in different ways. The lake is over 2 miles long, half a mile wide, and at its deepest is 12 feet. Now, I asked, if you've ever driven through southwestern Minnesota and you come upon a lake like this, it's a very surprising thing. Dry land farming all around you, and all of a sudden, boom, you see this lake. And I asked a farmer about that, and he said 100 years ago, they most likely tried to drain this. They were unsuccessful, and so it exists today. And that's true of much of our water resources down in that part of the state. Now, of course, the people down there love their water resources, and the Shakatan is a very popular lake. My well that I'll be talking about today is on the South Shore in Picnic Park, Lincoln County. It's a park that closes in the winter, so there's no de-icing issues. There's another well on the north side of the lake at a DNR boat landing. And the surface water samples are taken from a point equidistant between the two in the middle of the lake. And this area is dominated by dryland farming, feedlots. There is, I'd estimate that about 20% of the perimeter of the lake is settled. Otherwise, there aren't many people. The roads are mostly gravel roads. This lake was delisted in 2016 for eutrophic conditions, and it was a rare win in this part of the state. I think Governor Dayton even used it on his talk when he was traveling through the Southwest talking about water issues several years ago. And unfortunately, that status seems to be at risk now. And I'll be talking more about that in a few minutes. Now, at the start of the talk on the title page, I promised you that groundwater flows into surface water, and now I'm going to provide the proof of that. This hydrograph shows blue triangles, continuous monitoring of groundwater elevations, and in red, red diamonds, surface water elevations. Left-hand scale shows elevations above mean sea level. And a quick survey of this, and you can see that the blue groundwater elevations are always above the surface water. There are some gaps in the record. Of course, you can't get continuous monitoring of lakes when they freeze, and one of my transducers failed, so that's why there's a gap around 2017. The results from the northern well are very similar to this, showing continuous flow into surface water. Now, let's look a little closer. And I'm going to be using figures or arrows like this and lines. I normally parade around in front of a screen and wave my arms and point, but I can't do that. So I'm going to be using these symbols. So I'm now going to show you a close-up of this period, 6 months. And you can much more clearly see that groundwater and surface water are moving in concert, but also the groundwater is always higher than surface water. And that's an important point that I want you to remember throughout the talk, because you might have questions about what's happening, but if you remind yourself that groundwater flow is always into surface water, that surface water conditions do not affect groundwater, then more of this will make sense to you. There is I only have one well, or two wells around this lake. I can't prove to you that groundwater is flowing into the lake, but if you look at LiDAR, you can see that the flow is, that the elevations drop towards the lake. And there's also one point on the lake where we know that flow is out, and that's through the outlet to the Yellow Medicine. Lake Shakatan is the headwaters to the Yellow Medicine River. Okay, this is a cartoon that I made that just brings this home, cross-section showing groundwater is flowing past the well, and water rises up in the screen to the elevation of groundwater, and then it drops as it approaches the lake and discharges into the lake bottom. And this is the pattern at this lake. Now, I want to introduce the concept of transport. Water that falls as precipitation infiltrates to groundwater and then flows into the lake, and water can also carry dissolved compounds such as salt, which leads to this next slide. Left-hand axis is chloride concentrations in milligrams per liter, groundwater chloride concentrations in blue, and the lake in red. And groundwater chloride levels are higher at all times than the paired lake measurements through the 8 years of monthly sampling. And I should add, these levels of chloride in groundwater and surface water are considered low by state standards. My Madison Lake site features numbers over 1,000 milligrams per liter, but it's not the absolute value that I'm interested in today. It's the transport and what we can learn from this lake that can be applied to other lakes. Okay, now I'm going to change the scale and give surface water a better view here. So groundwater concentrations on the left, still in blue, but now surface water on the right, and you can see that the levels are below that of the groundwater. And you can see that that pattern of rising and falling of the chloride levels in groundwater is matched by surface water. And that's important for the next discussion here. You can see that groundwater and surface water are moving together, and groundwater flows into surface water, and the concentrations are always higher in groundwater and surface water. What else can we learn about this? Well, a close-up of several of the years of data. Again, both groundwater and surface water have their own axes. And you can see at this point, from May to June, there was a drop in chloride concentrations in groundwater, and that's matched by a drop in concentrations in surface water. And then you can see that in the rest of the year, the levels rise in both groundwater and surface water. And that's also true in 2015, where there's a drop from, in this case, May to July, I believe, and surface water. And then there's a little more complicated dance here that is matched from groundwater into surface water, and flow is towards surface water and concentrations are higher in groundwater, so you know that groundwater is causing this change in surface water. So this was a very surprising result to see this that clearly. Now, I'm certain that this one point in the county park is not the sole source of chloride to the lake, but it does appear to be representative of the movement of chloride through groundwater over a larger perimeter of the lake. And remember that this lake is completely surrounded by dry farming and feedlots, so it's not surprising that it might be representative. Okay, now this is the same data, but what I've done is I've averaged the monthly samples into a yearly sample. And so there's one red circle for all of the samples taken in surface water and a blue for groundwater. And you can see a nice pattern here. And by doing this, this allows me to quantify the relationship between the two data sets, and I'm going to use regression. And here's a textbook definition, because if I wing it, I'll leave something out. Regression is a statistical measurement that attempts to determine the strength of the relationship between one dependent variable and a series of other changing variables. And so what that means is, can I model surface water concentrations by taking just groundwater and applying an algorithm, an equation that predicts what the concentrations should be. And the expression of a good comparison is that you have a high R-squared value. R-squared is the square of the correlation. And by taking all of the full year data sets, I have an R-squared of 0.94, meaning that 94% of the variation in one variable may be explained by the other. And, you know, that is an unheard of, well, at least in my world, score for an environmental data set. Normally we are looking at much smaller numbers. When you get this kind of number, you generally pop a bottle of champagne and call all your friends to brag about your R-squared. And when I mentioned the water cycle earlier, I introduced the process that transport might work. Can we find evidence of this transport in the precipitation record?
What?
Okay.
I said no.
Okay, so let's go back to groundwater and lake levels. Researched the site in 2010. Average precipitation in the southwest Minnesota area was about 22 to 25 inches, total precipitation for the year. But it has been rising dramatically through the period of the study to 44 inches, and I'll show you that data in a second. What we're looking at here again is the hydrographs for groundwater and surface water. You know from looking at the water cycle that precipitation is driving groundwater, which is then flowing into the lake. But here's the funny thing about Shakatan. Even though precipitation is rising dramatically, groundwater and surface water levels have not shown much of a reaction. In fact, over the last 4 years, the level of the lake has been dropping. And so just as total precipitation was increasing by 15 inches a year, we're seeing this slow decline. And I can only assume that the outlet is capable of carrying large volumes of water and handled this just fine. But we lack a gauging station anywhere near Shakatan. Flow information would be crucial to trying to unravel this question. But to move on, this is the total precipitation for the town of Ivanhoe, which is very close to Shakatan. And you can see that, as I mentioned, the first 4 years, the average precipitation was in the 20 to 25 inch range. In the last 4, all 4 have been above 30, and the last 2 have been close to 40 or above. This is a trend that's been repeated, I think, throughout southern Minnesota, and it raises some interesting questions. My first thought was that perhaps this extra water was diluting chloride and causing levels to drop. You remember the drop in chloride levels in both groundwater and surface water. But the problem is that while that might be true of the lake, where water can easily flow into the lake at times of high precipitation, groundwater is filtration into groundwater. You can't push that rope. Those pore spaces are full. So when we get high intensity events, which really are what we're getting in the last few years, 1 inch an hour, 3 inches a day, that kind of thing, those pore spaces are full. And so water is shed in overland flow to the surface water. So we might see a dilution in the lake, but what causes the groundwater levels to drive the lake levels the way I showed you? It's clear the groundwater chloride levels are driving the surface water levels, but it can't be extra dilution. Well, there's another mechanism, and that is that total precip might be increasing, but it might not be increasing throughout all seasons. And I checked early spring, I checked late fall. winter, and all those rise with total precipitation. But here's a curiosity. Rainfall in the months of June, July, and August, when farm fields are turned over, when farmers are active in their fields, rainfall has been in decline. I can't tell you from this small amount of data that this is an explanation for why chloride might be decreasing, but right now I have no other explanation for all this data together. Now, next year, this year, if there's a big increase in rainfall in the months of June through August, we might learn something interesting about what's happening with groundwater. So yeah, I forgot I had these handy little tools because you couldn't see those trends, could you? Okay, so a sidebar. I've been making a case for collecting chloride levels in groundwater and in surface water, but not every project has access to monthly sampling. And that's why the groundwater unit is experimenting with downhole conductivity meters to see how well they estimate chloride. They're cheap and easy to deploy, and conductivity and groundwater temperature, which they collect, can yield specific conductance, which correlates with chloride. And that's what this display on the screen shows. It's a professional paper by Hans Stefan using our data at the MPCA to show that there's a very high correlation between specific conductance and chloride for Minnesota waters. And you now are fully educated on how to read R-squares. That's a very nice R-squared value. Back to the conductivity meters. The ambient network has, I think, about 24 of these meters deployed, and I have 4, including one at Shakatan. And they were all installed in 2018. And another advantage that I've just realized about conductivity meters in the time of COVID is that currently our field crews are not allowed to go out and take samples. So it's possible that we'll miss several months of sampling that would tell us what chloride concentrations are doing in the lake and in groundwater. But we do have these conductivity meters, and I can go at some future point and download that data, and that will tell me give me a good estimate of chloride. So there's one advantage that we have going for us right now. Okay, going to the conductivity data. Here's Shakatan data. Groundwater chloride values as blue triangles on the right-hand axis and red circles from the conductivity meter in the well on the left-hand axis. Now I'm converting this to specific conductance measurements. The data appears to line up pretty well, though I recognize that all that extra data from the specific conductance kind of gets in the way of comparing things. So what I did next was pull out the conductivity measurements that were taken after the well had been purged while the sample was being taken, so that we'd have a real apples to apples comparison. So I'm taking these points on the out of the larger data set. And then this allows me to quantify the data and do yet again another regression. So here's a simplified view of the Lake Shakatan data where the chloride value is matched with the downhole data from the time of the visit, using the same, and they have the same axes. I haven't yet visited the well to determine what the conductivity values are for the late fall chloride measurement, but I fully expect it will line up well. This R-squared value of 0.89 lines up very well with the published value that I showed you a few slides ago. And it is also a very good number. It isn't 0.94, so maybe you have a Pabst Blue Ribbon and you call your mom, but it's still a very good number. Okay, now the final piece of this is phosphorus, and I'm really going out of my comfort zone with this, but I found this to be a very interesting story and I wanted to share it. And I think I have data to back up some of my suggestions here. There's an interesting story with some tragedy involved about Shakatan because there's a precarious balance between eutrophication and the expectation of homeowners who live on the lake. Excess phosphorus enters the environment from fertilizer, manure, wastewater treatment facilities, and industrial processes. And as it happens, the DNR and the MPCA have worked for a long time to delist this lake for eutrophication impairment. Shakopee remains a good example of how a lake can improve, but we're still writing the chapters on this story. This display here reveals the results of a survey the DNR did back on the lake in the year 2000, checking for surface water or surface aquatic vegetation to a grid. So they had created a grid ahead of time, went out to the lake, went to those grid nodes, and registered whether there was aquatic vegetation at the surface. If there was, they made a mark. So you can see that the open spaces are areas where there was no vegetation found. Now compare that to results from a similar survey in 2018, where aquatic vegetation is much more common. Shakopee in 2018 had lake-wide aquatic vegetation. This data is all thanks to Donna Perlberg, from a DNR aquatic plant ecologist, for the data and for her explanations. And her description of collecting this information reminds me that fieldwork can be a wonderful break from office work, but it can also be tiring, cold, and never-ending. And it's good to spend some time collecting data. It's good to get out away from your computer and go out and collect data, because it means that you recognize the hard work that underlies all this wonderful data you use in your job. And what Donna told me was, after a couple of years of very little aquatic vegetation, she took a new student worker out, and she told the student worker, oh yeah, don't worry, this will be fast and easy. We just have to check these grid nodes, and we'll be done by, it's an 8-hour day, it'll be fine. And fieldwork is wonderful, but we've all had those days where things don't match up well. Well, they got out to the lake and aquatic vegetation covered the lake. They had a 14-hour day. The student was wondering if he had made the wrong choice of a career. And it turned out to be wonderful news for the lake, but it is a lot of work to collect. So you can take that aquatic vegetation coverage and you can turn it into a chart. And that's what I've done here. So you see in blue circles, aquatic vegetation on the left-hand axis, and the percent of aquatic vegetation. Note that the percent coverage was at 30% 10 years ago and reached almost 100% back in 2016, and now it's in decline a little bit. Secchi depth, the green diamonds, axis on the right, aquatic vegetation can be tied to lake clarity as measured by the MPCA-led Citizen Monitoring Program. Depth to where a Secchi disk can be seen from the surface. Well, maybe some of you don't know what a Secchi disk looks like. Luckily, I'm prepared. This is a Secchi disk. Volunteers, usually people who live along the lake, go out once a month or more often. They slowly lower this over the side of the boat until they can no longer see that pattern. Then they pull it back up slowly until they can just register it, and they mark that down as the Secchi depth. So the DNR will tell you that aquatic vegetation plays an important role in a lake's health. And what we see here is that this correlates with the Secchi depth. So if you look at this data here, you can see that the blue circles showing that there was like 25% of aquatic vegetation detected in 2009, 2010 is matched by a low Secchi reading, right on the right-hand axis, of about 1 meter. Then as Secchi depths increased to over 2 meters, so clarity was up to 2 meters when they picked up the aquatic vegetation surveys again, they found that they very high percentage of aquatic vegetation matched well with clarity. So these two are related, and I'll use this relationship going forward here. Unfortunately, aquatic vegetation is not always appreciated by the public, many of whom prefer open water for their boating. And this led to a management action at Shakopee and the killing of vegetation by chemical means in 2019. Now, chemical treatment of weeds, as they call them, can release phosphorus from the dying plants, which then can contribute to the growth of other plants and algae and also allow more sun in to strike the bottom of the lake. Coincidentally, the lake suffered one of its worst algal blooms after the treatment last summer. So this is an aerial photo taken by the DNR showing a lake-wide bloom with no surface aquatic vegetation visible at this time. Now, the bloom can't be definitively laid at the feet of the chemical treatment, but it undoubtedly was contributed to it. Now, the DNR has its hands full educating Minnesotans on the importance of aquatic vegetation and the role it plays in maintaining a healthy lake. But it's a difficult game they play because they are in charge of stocking lakes and managing lakeshore development and other fisheries subjects. So last year's treatment and the bloom were a blow to efforts at stabilizing Shakopee as a healthy lake. How does what happened relate to detected phosphorus in surface water and groundwater? I have some data that might shed some light on this question. I'm starting with the Secchi depths again, and this time I've flipped the axis so that as you go down, the Secchi depths increase. So clarity increases as you move down. And now here are lake phosphorus values on the right-hand axis, blue triangles. Phosphorus values decline as clarity increases, and phosphorus values rise while clarity decreases. I didn't submit this to a regression analysis. It's noisy data, but you can eyeball this relationship in yourself. And after 10 years of declining phosphorus levels, the last 2 years show a reversal. So maybe you're thinking, is this change in phosphorus caused by inflow from groundwater? The short answer is no, and the longer answer is it is complicated. We only have a few data points to use to decipher this mystery. Groundwater phosphorus levels are in red. After 4 years of groundwater phosphorus concentrations matching surface water phosphorus, the two diverted. Groundwater phosphorus levels dropped and surface water levels rose. So whatever is causing the phosphorus levels to rise, it doesn't look like it's related to groundwater. And if the chloride example holds for phosphorus, this increase in lake phosphorus isn't from changes in land use application either. It's likely something that is happening in the lake, and I'll leave that mystery to the smart folks in the water monitoring section and the DNR. And if you're wondering, I only have 7 years of groundwater data because I put the wells in Shakopee in 2013. Full years. Okay, last slide. Can we tie this all together? Chloride and phosphorus. Groundwater phosphorus concentrations on the left-hand axis, gray box. Groundwater chloride on the right hand in red circles. Now, this isn't like comparing groundwater and surface water concentrations of chloride where so much is shared. This is comparing two different constituents with different sources, solubilities, groundwater travel times, and yet they seem to follow a similar path. Now, obviously more work needs to be done with phosphorus, but it appears that this is a result worth investigating further. So, in summary, groundwater is more than an urban concern. Combining resources from the Environmental Outcomes Groundwater Network and the good folks over at the Water Monitoring Program produces an effective tool for studying the movement of compounds through our groundwater and surface water. Chloride is being transported from land through groundwater and into surface water, and Shakopee is not yet a stable lake. Thanks for your attention.
Hey, Andrew, while you were going, we did have one question in the chat, and now that we've ended, folks can feel free to, I think it'd probably be best to maybe put your comment in the chat, and then either I can unmute you or ask the question for you. But we had a question on here of who did the chemical treatment on the aquatic vegetation.
I kind of made that a fuzzy point, didn't I? It is possible for lake owners to get approval for treatment by moving higher up in the management column at the DNR than the folks that are studying the lake and often understand the lake very well. So this was a decision that was approved, I believe, by the DNR, but was not carried out by the people that do this work.
All right, we've got a question here from Jim Berg. So a lot of chloride and phosphorus is from fertilizer?
That's one source.
Yeah, and I will just add that potash or potassium chloride, I'm sure we've all heard of that. That is a very common, that's that chart that Andrew showed at the beginning. That's the main source of chloride from fertilizer is potash or potassium chloride.
It's nice to have you on board.
All right, what else here? Oh, Mark, that was you. Mark is asking, phosphorus is going to bind to calcium in soil, unlike chloride. It will be difficult to make that comparison.
And yes, I recognize that there are some differences. I'm only looking at the data and wondering if this is worth studying further. But for now, we have indications that that phosphorus is behaving somewhat similarly to chloride, but I am not a geochemist and I'm out of my depth.
Well, I'll just say that since your study includes chloride, yes, of course you should continue it.
Thanks.
All right, Mike Trojan here. If Mike, you want to unmute yourself, you can go ahead and ask your question. No? The SC chloride correlation has a lot of potential in urban areas where groundwater may depress surface water concentrations in winter, but elevate them in summer. Thoughts?
Could you repeat that, please? I had a technical issue here.
Yeah, so the SC to chloride correlation, SC specific conductance.
Okay.
Specific conductance.
Chloride.
I mean, that's what I'm inferring here. Has a lot of potential in urban areas where groundwater may depress surface water concentrations in winter, but elevate them in summer. What are your thoughts?
I think that other people have looked at this subject more than I have. I wanted to show that our use of conductivity meters was warranted and that we should roll out more to collect more of this data. And so I've started to look through our data to support the Shakatan data, but I haven't looked at seasonal effects and haven't looked at the published recommendations. So.
Then we've got, maybe you are heading this way, Andrew, but how do you know the overland flow of chloride, which is also entering the groundwater, is not the primary contribution to the lake? Groundwater / surface water concentrations would still be paired and have a high R2.
It could be, and I pointed out that in this environment with high intensity rainfall events, that groundwater is not going to be receiving anywhere near the increased flow that surface water will. I'm just looking at the results, and the results seem very clear that groundwater concentrations are driving surface water concentrations. So if you hang on to that lifeline, then you can look at this issue of what's happening with concentrations in overland flow, and you must assume that it's representative of the concentrations that are going perhaps into groundwater. That's my quick and dirty analysis of that.
I'm just thinking here about septics and wondering if there is if a phosphorus and chloride connection maybe exists from septic systems, considering that I'm sure the hardness of the water in the area is high, and there's probably a lot of water softener use in the community, and most of them are on their own septics. I'm wondering if there's any evaluation into the condition of the current septics and what's kind of flowing out of those septic systems and making its way.
Yeah, and again, I acknowledge the sources, but can't parse them out. Um, we're looking for general relationships that can be used to guide future studies, and that's an interesting question.
Scott has a question. Did you want to unmute, Scott, or would you like me to ask it? Let me try unmuting him. Scott, you're unmuted.
Okay. Can you hear me now?
Yep.
So my question, Andrew, is I was looking at your groundwater concentrations of 10 milligram per liter, and when I've looked at drinking water wells in that part of the state, chloride is typically less than 5 milligrams per liter and sometimes non-detect, less than 1. And, deep, those wells are very deep, hundreds of feet deep, and they're kind of they represent the water that's been in that area, over the past hundreds to thousands of years, as far as I understand it. So the 10 milligram per liter chloride concentrations are actually pretty high. It seems like it's higher than what might be there naturally. Have you done any thinking about what the natural background chloride would be in that area, and whether that groundwater 10 milligram per liter in the kind of that lake right next to right next to the South Dakota border is that higher than what would be there naturally? If you can even answer that question.
Yeah, let me try. Remember that we're talking about water tables, and we're talking about shallow wells. And so these are going to be more vulnerable to uh, groundwater infiltration that occurred just within a mile and within years. The water that you're talking about is probably aged 1,000 years or hundreds of years in any case of age. That rainfall that recharged those aquifers fell hundreds of years ago. The rainfall that recharged well I referred to could have fallen just years ago, and it was intentionally placed to intercept flow from farming practices or from human activities. So that would be a very different level. But you also have to remember that well, don't have to remember it at all. Geologists might remember it. Southwest part of the state has some Cretaceous that typically is saline-rich water, very old water, but it's you start to get into issues of how old is the water, what is the geochemistry of that old water, and you'd have to do a pretty careful study to try to answer your question in more detail.
It looks like Sherry, you've got a question. Maybe you want to ask that, or you want me to? She's asking, have you computed the chloride to bromide ratios in the groundwater samples?
Yes, and it comes out to be on the dividing line between natural and human influenced concentrations. So you can use that ratio to determine if water is, the salt is from a natural background, or is it introduced for de-icing, by de-icing in farming practices. And this ratio is right in the middle. So it's kind of mixed bag. You can choose whichever way you want to go on that.
And there's two questions. I'll actually ask the most recent one is, what cut do you use for the chloride to bromide ratio? What value are you using for the break? Those so two similar
250.
questions.
Ratio of 250.
Okay. And then we have a question here from Phil. Are there measures of other associated ions like sodium, potassium, CO3?
I looked at those when I started. I mean, the chloride was an easy start. I wanted to know what was happening with chloride. Phosphorus is another big concern for the state, and so I added that. I haven't looked at the others. It's a next step, obviously. We could go in that direction, but I haven't yet.
It seems like maybe the potassium might be a good one if that's the for at least for chloride. That's the linked might be a
Right.
correlation there between the potassium chloride or the potash fertilizer being used in that area. Any other questions here? Well, this was a really great talk, and I really appreciate everybody joining us. We had about 148 people. I think that like might be a record for even
I
used to
think
have
it is actually. Andrew, thanks so much for being game today. It was a great presentation. Thanks a lot.
Thank you very much. I had a lot of fun. And people can contact me if they have other questions through email.
Thanks, Andrew. Appreciate it.
Thank
Thanks.
you.
Bye-bye.
Thanks, Peter.
And we will have another water issues talk in I think 2 weeks there. Mark, is that our next one?
Yeah, our next talk is May 14th, and we are going to be hearing from Rebecca Higgins in our remediation section. She's going to be talking about the PFAS contamination in surface water in the metro area that she's been working on for a while. That should be a very interesting and engaging talk.
Yeah. All right. So, well, everybody, hopefully you'll join us on May 14th. And thanks for being with us today. And we'll hopefully talk with all of you, maybe see some of you virtually soon.
Thanks a lot, Brooke.
Thanks. Have a great day, everyone.